Making thin water films. For wet chemistry lab operations on space station, we need the equivalent of a zero gravity beaker. What we are using here is a 4-inch square Ziploc baggie, which makes a two-dimensional beaker where the opening is a slit instead of a round surface. And you can squeeze the bag to open it up a bit so you can have access to this surface. The slit part of the opening allows surface tension forces to contain the liquid so it won't slosh out and it will be well behaved. Here we're taking a 50 millimeter wire loop and dipping it into the water in our two-dimensional beaker. Now this water is deionized water. It's the purest water we could find on space station. There is no added surfactant. In the process of pulling this wire loop out, you draw out a sheet or film of water, not unlike what you would do on the ground with a soap film. This solution has no soap added to it. You can use surface tension forces to drain this film, and it will be about 200 microns thick. Here's a view of this film with reflected light, and you can see there are no interference colors. This film is too thick to show interference colors. It has sufficient mass so you can drive it into these delightful oscillations where you get these lensical structures forming on each end of the oscillation. Once in a while you can spall off droplets of water, which we will be able to see in high-speed digital still images what the water looks like while it is being driven off of the film. These are similar to, however different, than splashes you would see from droplets splashing under the influence of gravity. Here we have a film caught in the middle of being ruptured. Diffusion and convection. Once you make these films, they make a delightful two-dimensional sheet of water in which to do other experiments with. Here we are using food coloring to look at the role of diffusion in a two-dimensional sheet of water. And the food coloring drops just stay there, and you can slowly see the effects of diffusion making the edges fuzzy. You can puff air on this sheet like we are doing here with a syringe, and you can move the food coloring around. This movement makes a nice sharp edge. When you quit puffing, viscous forces dampen the motion, and you're just left with this structure. This is a panaway in our wet chemistry lab, which is set up in the Russian FKB module. For our video background, we use one of our cleanest dirty towels, or for the blue background, we'll use one of our cleanest dirty shirts. Here we are panning edgewise onto this sheet to show indeed it is very much a two-dimensional structure. These sheets are quite stable. We've kept them around for well over a month if you retard the evaporation, which tends to thin them. Now here is this sheet with the food coloring after about an hour, and you can see the edges are fuzzy due to the effect of diffusion, which operates rather slowly. If you puff on it, you incite convection due to the bulk fluid motion, and that sharpens the edges once again. Now, we're going to investigate tracer particles with induced convection. These are mica flakes, 5 micron diameter, in a water suspension. We put a couple drops on one of these sheets, and now we are intentionally inciting rotational flow within the plane of the sheet by giving it a little stir. And this motion now, this rotational motion, will continue for about a half hour before viscous forces dampen it down. And we're seeing streak lines being left by the tracer particles. And we will soon go into a time-lapse mode here where about 10 seconds of playtime is equal to 1 orbital period of 90 minutes. You can see that the pattern rotates in one direction for a while. It'll stop and start to rotate in the opposite direction. This is due to the residual acceleration forces on space station. You can also see that diffusion is slowly making the streak lines diffuse with time. So now the question is, what can we use these for doing other fluid mechanic experiments where you can capitalize on having a two-dimensional sheet of water for doing fluid mechanic experiments? Marangoni convection. Here we have a stationary series of streak lines left from the mica flake tracer particles, and we bring a soldering iron up to the edge of the frame. The soldering iron imparts a temperature gradient on the fluid, which in turn gives a surface tension gradient, and the surface tension then plays tug of war and makes a convection happen, as you can see here by watching the tracer particles. This is sometimes referred to as thermocapillary flow as well. We can drive Marangoni convection simply from the heat from a flashlight. You need to know about Marangoni convection whether or not you're really interested in it, because this could drive unwanted artifact in a microgravity experiment, say by just shining video lights onto a diffusion experiment. Here we are directing the energy from the flashlight in the center of the water sheet, showing that you can incite Marangoni convection without having the presence of the frame. Thin film crystallizer. Here we have a thin sheet of sodium chloride solution and time-lapsed video showing the growth of sodium chloride crystals over about a period of a day. And the fluid mechanics and the kinetics of crystal growth here is restricted to 2 dimensions. These crystals have a resulting thickness of about 1/10 of a millimeter. Here we see another crystallizer, nucleating crystals. There's one area on the right-hand side of the wire that is a hot spot that consistently nucleates crystals time and time again. The sodium chloride solution came from the galley. Instead of a salt shaker on space station, we have a sodium chloride solution so we can squirt the salt water on our food, and it makes nice science experiments. Here the crystals you see are about 15 millimeters on an edge. And you have a combination of hexagonal plates and squares. Here it has evaporated to dryness, and you can see the same crystals. You can harvest the crystals by reaching in and pulling them out. And again, they're about 1/10 of a millimeter thick. Here we are making a thin film out of protein. Now this film happens to be blueberry flavored, and you might suspiciously think it's Jell-O, but nevertheless it is still protein. And it is interesting in terms of what you can do with films like this, which will harden with time. And here the film is being made. Most of the bubbles are being excluded by the drawing process. After this film hardened, we used it to suspend some droplets of sodium chloride solution, just as a demonstration for what you might be able to do with a protein film. If you had the right chemical constituents, you could use it to suspend little chemical reactors where you could have diffusion reactions going on between the film and these reactors. And here we're just showing a time lapse of sodium chloride crystals growing while they're suspended by this protein film. This film has sufficient integrity that you can snip it out of the frame with a pair of scissors, and then you can put it in a baggie and you can bring it back home if you like. And again, this is representing what you could possibly do with films made of proteins or other materials in a weightless environment. Here is a two-dimensional sheet made of sugar solution, and it became saturated with time and started to grow these needle-like sugar crystals. And over a period of about a week and a half, the crystals grew and filled in the whole frame. Nucleate boiling. Here we use a soldering iron to instigate nucleate boiling within a sheet of water. These sheets have to be a little bit thicker. They're about 4 millimeters thick. And when the tip of the soldering iron is submerged into the sheet, it immediately drives rather violent convection, as you can see here. Bubbles will form on the tip of the soldering iron, and they will be whisked away by this convection and leave a free surface for more water to be in contact with the tip and make more bubbles. Here is the soldering iron submerged up into the barrel, which is about 15 millimeters in diameter, and this was to provide simpler geometry than the conical tip. And here you can see bubbles forming on the surface of the barrel. They expand, they move away, they are whisked from the surface, and new water moves into its place and is heated and forms more bubbles again. To first order, this doesn't look that much different than watching water boil on a pot sitting on your stove down on Earth. Here we're moving to more of a spherical geometry where the barrel of the soldering iron is wet with a spheroid of water, and we can watch over time as boiling is developed. And again, the bubbles move from the surface in the absence of gravity-driven buoyancy and gravity-driven convection due to other means, and they move around, expose the surface to new water, and you have boiling that does not look that much different than boiling in a pot on your stove. Interlude, tea break. We follow Russian tradition on Space Station and have tea breaks. And here we have a bag of tea with a straw that you normally suck the tea out from the bag with. And we're using our chopsticks to eat the tea, a rather elegant way of eating your tea in a weightless environment. So here's a close-up showing the straw with a sphere of tea coming out. And you can just snag that sphere of tea with your chopsticks. Again, surface tension is your friend in a weightless environment. And then you can just eat your tea with chopsticks. Here we go. Whoops, you spilled a little drop, no biggie. You just grab it with your chopsticks. So on station, you can eat your tea with chopsticks. A rather elegant way of doing that. And here we're opening a can of the Russian honey, Miot. There's no Velcro on this can, so there's no way to hold it to the table. So again, we use all this surface chemistry we learned in college, put it to good use here. We put a drop of water on the bottom of the can. And then, voila, you stick it to the table and away you go. Making water spheres. Up till now, we've been looking at sheet, two-dimensional geometry, and now we're moving to three-dimensional spherical geometry, and we're going to show 3 ways to make a sphere attached to a loop. First, we start off with a standard water sheet, and we just add more water to it and puff it up into a full sphere, as you are seeing here. All these spheres are made with the 50 millimeter diameter loop. Second method is to just add water to the loop until the sphere bloats up and touches the loop all the way around and gets locked in on its diameter chord. And until that happens, it's rather precarious. It's really easy to lose this sphere of water. And watch what happens now as it gets larger and larger, and eventually it gets locked in by the diameter hoop, and then it's going to stay put. And once you have this water sphere locked in, you can move it all around and do all kinds of other things with it. Here we're going to just lasso a free sphere of water with the loop. You can draw some of the water off with a towel, and you will end up with a non-spherical shaped object like you see here in profile. I guess you could call this magnifier a meniscus lens. Vortex rings. Here we have a 50 millimeter diameter sphere of water, and we're going to touch a small drop filled with tracer particles to the back and look at the mixing pattern. We were amazed to find a vortex ring forming. However, after we made this observation, we could use our surface chemistry and explain why the vortex ring formed. And this is an example of why we do experiments in the first place, particularly those that you don't know what the answer is going to be before you do the experiment. Once you see what the behavior is, then you can use existing knowledge to explain what goes on. Here we have the needle shoved through the interface, and we're injecting the same tracer particles, and it looks more like what you see in a smokestack belching out smoke. Large water sphere. Here we are going to make a large sphere of water about the size of my head, 130 millimeters in diameter, and we are going to put a puff of air, 10 cc's in 100 milliseconds, as a delta function spike against the side of the sphere, and we're going to look at the resulting waves. And this is real-time oscillations. It's a delightful combination of surface waves and body-centered spherical waves, all running back and forth in this spherical oscillator. And this was another one of these jaw-dropping moments where we had no idea what was going to happen until we did the experiment, and then we're left scratching our heads trying to figure out why it behaves this way. Here's the same scene in slow motion. Look at that. A variety of surface waves running around, sort of like throwing a rock in a spherical pond, and the waves are forced to converge at the antipoid, and then a spurt goes out. Surface tension makes them collapse back in, and it sends a ripple of waves back the other way. Meanwhile, you have body-centered waves or inertial waves going through the center of this sphere, and everything you see then is a delightful superposition of all of these waves until viscous forces dampen everything. We will see this one more time in slow motion. Look at the drop of water spalled off from the initial impact. When we saw this, we couldn't help but think about computer simulations where some hapless planet gets whacked by an asteroid. Symphony of spheres. Here we have about a 3-inch diameter sphere of water with an 1.5 inch diameter bubble inside, and we are adding more air to the bubble, and in the process of doing this, it drives the bubble into some delightful oscillations. And realize this is the inverse system of what we just saw with the large sphere, where here we have a sphere of air surrounded by water. In the previous example, we saw a sphere of water surrounded by air. Now, watch at the end of this experiment. We will drive an oscillation, and after we quit putting in air, look in the center of the bubble, and what do you see? When we saw this, again, it made our jaw drop, and so we decided it was time to inject droplets directly into the bubble. So what we have here are droplets in a bubble in a sphere, which is why we call it our symphony of spheres. And we can look at these delightful interactions between these droplets bouncing around in a three-dimensional billiards game, where they interact with collisions with each other and collisions with the wall. And sometimes there is mass transfer between the droplet and the wall, or between two droplets. So why do we get the mass transfer with some collisions but not other collisions? And where does the momentum come from that propels these little drops? Watch this droplet. It will bounce 5, 6, 7 times, and then it will have a mass transfer, and it gets momentum from that mass transfer, and it gets jetted off the surface, and it bounces around inside of the bubble until eventually there will be another mass transfer and the remaining part of the droplet gets jetted around again. Now, there was a droplet that had a mass transfer, and now we will see this mass transfer across the interface in slow motion. Notice that the mass transfer drove the bubble into a series of spherical oscillations, not unlike what we were able to do previously. Here is a droplet rolling on the inside of the bubble. Watch what happens. Here's another droplet. It is rolling around on the inside of the surface, and the angular acceleration from circular motion that will keep the droplet in contact with the inside of the bubble, and it'll just continue to roll and roll and roll and roll. And we would have droplets roll for 45 seconds, sometimes 60 seconds, before a mass transfer event through the interface would propel the droplet away from the surface. Here's a droplet rolling in and out of the plane of the video. So a rhetorical question, is this droplet rolling like a ball across a carpet, or is it sliding like a hockey puck? If it rolls, it connotes some level of friction. Now we're using food coloring as a tracer to look at the flow into the sphere of water beyond the bubble. And notice that the flow field into the sphere makes vortex rings, which is not surprising considering what we learned before. Watch this droplet. It is filled with mica flakes, and you can see that it looks like this droplet is rolling. Here we have another rolling drop, but notice it is rolling 90 degrees to its direction of circular motion. So from this we conclude that these droplets are sliding like hockey pucks, and they may have some initial rotational momentum. Here you can see the tracer particles forming what look like polar cap clouds outside of the bubble. Here we have a rotating sphere of water about 25 millimeters in diameter, and inside this sphere are a whole bunch of little tiny air bubbles. And we will see what the angular acceleration due to rotation does to these air bubbles as a function of time. What you are observing are the bubbles moving to the center axis of rotation. As a function of time, they will form this rather tightly packed bubble core. These bubbles are kept from coalescing from a small amount of added surfactant to the water. Here we have a rotating sphere filled with bubbles and tea leaves, and as expected, the bubbles go to the center and the tea leaves go to the outside edge, along with a few chunks of orange peel. Here we have a rotating sphere with bubbles and chunks from breaking up a small vitamin tablet. And the bubbles go to the center core, but the vitamin chunks seem to stay in their location dispersed through the sphere. And from this we deduced that the vitamin chunks have a density near that of water. Here we have a 250 milliliter culture flask filled with water and bubbles. We will give it a bit of a spin, the bubbles will quickly form a bubble core as expected. However, we get these delightful patterns that form within the body of the fluid from the dispersed bubbles. These patterns will spontaneously form, and then after some time they will abruptly disappear and then reform in a whole series of pattern oscillations. We did not see this oscillating pattern formation in a simple rotating sphere, so we speculate that this has something to do with the boundary conditions set up by having a rotating flask. Watch closely here. You'll see the patterns form, and then you'll see the patterns disappear, and then they'll reform. Now look at the patterns here. The leading edge is diffuse, and the trailing edge is sharp. You'll also notice we have some of our cleanest dirty shirts for the backdrops again. Here we stop the rotation and disrupt the bubble core. Here we are going to place an effervescent antacid tablet into a sphere of water. Look at the resulting bubble dynamics. You get chemical reaction at the surface of the tablet with the water forming bubbles. The bubbles can get kicked off of the surface with some degree of momentum, and they travel out into the fluid where they can collide with each other, and then they rapidly coagulate and form larger and larger bubbles. This appears to be a bubble war in its own little bubble world, and the large bubbles appear to be able to eat the smaller bubbles at a faster rate than the smaller bubbles can eat other bubbles and grow. So you are rapidly dominated in a bipolar world here with one or two major superbubbles. Here we're going to see this again, and watch closely how rapidly the bubbles form at the solid surface. They move out into the body of the fluid, and they rapidly agglomerate and coalesce into larger and larger bubbles, and these larger bubbles continue to eat the smaller bubbles at a faster rate than the smaller bubbles can eat other bubbles and grow themselves. And here you have a situation with a few large superbubbles. And they will eventually grow to the point where there's only two superbubbles left. And now you can see between the two superbubbles. And eventually you get to a state with only one superbubble, and all the others form an annular space that almost looks like cloud cover. Being engineering types, we wanted to see if we could remove the bubbles. So we sucked the gas pocket out, and now we stir the sphere into rotating motion, which will form a bubble core, and we can selectively remove the gas pocket using a syringe. And if we work at this long enough, we can eventually remove most of the bubbles and end up back to something close to what we started with. Here we're removing the last little bit of the bubble core. Now we're going to absorb the sphere onto a towel using capillary action, and the water will form a rather thick layer on the towel as capillary action makes it move out throughout the body of the towel. Viscoelastic fluid. Here we have a liquid bridge of viscoelastic fluid whose length is less than pi times the diameter, and it sits there stably. Now the length of the liquid bridge is greater than pi times the diameter, and this time-lapse video shows the onset of the Rayleigh instability, which breaks the column into 2 drops. Here we squirt the viscoelastic fluid out a nozzle that is about 2 millimeters in diameter, and we can see the onset of dye swell where the diameter of the liquid stream puffs up by about a factor of 2. The time constant for the onset of dye swell is sufficiently slow compared to the fluid velocity that we can see this detached dye swell shoulder. If we slow down the velocity of the fluid, the dye swell shoulder will move up and attach to the nozzle. If we increase the velocity of the fluid, the dye swell will be pushed further downstream. Here we show some observations with a rotating bolt, but first we show a few clips of how we make one of these videos, and you can see in the background is one of our cleanest dirty shirts. So here's a rotating bolt, and it's going to collide with a tabletop and exchange momentum. And we can see a delightful interplay between linear momentum and angular momentum. So watch this bolt. It is rotating fast and translating slow. It will suffer a collision, and now it is rotating slow and translating fast. Delightful interplays. And we will show many of these collisions under the philosophy that you can never have too many collisions like this in which to observe. And again, there's nothing magic about observing this momentum exchange in weightlessness. It's just you can see it without artifact from gravity. Gyroscopic platform. Here we have a compact disc player, and the rotating music disc inside presents a fair amount of gyroscopic stability. Here's a compact disc player turned off, and it freely tumbles about its center of gravity. And here's one turned on, and again it shows gyroscopic stability. Being engineering types, we decided to tape 2 together, and when they're turned off, there's no stability. But now that they're turned on, they make a nice 2-axis gyroscopically stabilized platform. Again, being engineering types, the next thing we decided to do was to tape 3 of them together, and here they're turned off, and it freely tumbles about its center of gravity. Here they're turned on, and it exhibits a fair amount of stability as a 3-axis stabilized platform. I had one student ask whether playing heavy metal would give more stability, and I don't think so. The next thing to do is figure out how you could use it. So we taped our flashlight to it, and when we work at dark corners of station, like with our drill driver, we can use the platform as a third hand, and we can get to work with our drill, and we can listen to music at the same time. Bubble motion in microgravity. Here we have a flask filled with water and bubbles, and we are seeing the bubbles move under the influence of microgravity at about the 1.5 to 2 micro G level as a function of time in this time-lapse video, where 15 seconds of playtime equals 1 orbital period of 90 minutes. Here the station is in XPOP attitude, which is a solar inertial attitude, and look at the motion of the bubbles. They tend to move around in a circle. Now look at local vertical, local horizontal, which is an Earth-oriented attitude. And now look at the resultant motion of the bubbles. They move horizontally, and then they move diagonally toward the right-hand corner. So the motion of the bubbles depends on the station attitude, which affects the direction and magnitude of the residual acceleration at the micro G level. Here we're in local vertical, local horizontal, with the flask in a different orientation, plus y in the velocity vector. And now the bubbles predominantly move in the upward direction. So again, what we learn is even at the microgravity level, as a function of time, you can impart significant velocity to particles, and the direction depends on the attitude of station. Particle agglomeration. Here we have a gallon-sized plastic bag filled with 1 millimeter diameter sodium chloride crystals. You shake this up, and the individual crystals will rapidly form agglomerates, and these in turn form floccules of the order of several centimeters on a side, and all of this happens in about 10 seconds. Here is a slow motion view of the same thing, showing the individual crystals rapidly forming agglomerates. And again, these form floccules, all within about 10 seconds. Here we see a 2 to 3 centimeter sized agglomerate that is impacting the wall at about 1 centimeter per second, demonstrating a rather strong cohesiveness to hold together. And here we have sodium chloride crystals 4 to 10 millimeters in diameter, and these exhibit the same traits as we saw with the smaller crystals. They rapidly coalesce and form agglomerates and floccules that are several centimeters on an edge. This is a bag of Russian tea. And mind you, it's not a tea bag, but a bag with a tea bag inside. And there's a generous dose of sugar, about 1 millimeter diameter crystal size. And you shake this up, and you see a similar behavior with this organic crystalline solid as you do with the inorganic sodium chloride crystals. They rapidly form agglomerates, and these agglomerates come together and form floccules. Here is a close-up showing the role of electrostatic forces in shaping these agglomerates, and they move around. They will be attracted to the wall. Charge will be transferred, and the agglomerates will be expelled from the wall in the opposite direction. Seeing these crystals move around reminded me of some kind of microorganism, perhaps the sea monkeys I used to have as a kid that you'd order from the back of a comic book. When you tap the side of the bag, you disturb the electrostatic forces and you form a spot where the sugar crystals are attracted. Here we have a bag of coffee, about 100 micron diameter freeze-dried coffee. And again, we see the same behavior here, rapidly forming agglomerates and floccules within about 10-second periods. This is a flask of water with 5 micron diameter mica flakes suspended, and in a period of several weeks, these flakes will come together and form large floccules, centimeters on an edge, in a self-similar manner that we saw with particles suspended in the gas phase. Rotating bodies. Here we have a rectangular solid rotating about one of its axes. There's a minimum moment of inertia and a maximum moment of inertia, and it will spin stably about either of these axes. If you spin it about its intermediate moment of inertia, it will not spin stably, as we can see here. Now, what about a cylinder? Here we have a solid cylinder, and it will spin stably about its long axis. Again, another solid cylinder, give it an axial spin, it spins stably. Here is a liquid-filled cylinder, an axial spin, and it will not spin stably. It will change its axis of rotation and tumble end over end. Here is another liquid-filled cylinder, and again, it will not spin stably about its long axis. It will change its axis of rotation and start tumbling end over end. Here is a long cylinder, and it is liquid-filled, and it spins stably about its long axis until, of course, it impacts a hatch. What do you think would happen if you were to spin a fresh egg and a hard-boiled egg, only they're not confined to a tabletop? We're going to do this and see if you can see the difference. One of these is a fresh egg, one of these is a hard-boiled egg. So will future space colonists be able to tell the difference between their fresh eggs and their hard-boiled eggs by giving them a spin? Watch repair. My watch on orbit broke. The crown broke, which controls most of the functions of this particular watch, and then one of the buttons came off. Eventually we found the button. It was stuck against a filter on a ventilator, and now that we had all the parts, we decided to take it apart and fix it. And part of this was to demonstrate that on orbit you're not just a bull in the china closet. You can indeed do fine motor skilled repair work, and taking your watch apart, fixing it and putting it together again is sort of a paragon example of this. And dealing with all these little tiny pieces is not as difficult as you would first imagine when you are in a weightless environment. You just work slow and careful, and you can keep everything corralled. Every once in a while there's a surprise. You could float the guts of the watch out. There we are, and we will deal with that later. The button came off because it was fastened by a screw from the inside, and so it's rather easily repaired. We put it together, and we always use the right tool for the job here, which on a Frontier is any tool you can find that you get the job done with. And so we got the button installed and the screw tightened up. And now we need to take the guts of the watch apart so we can get into where the mechanism that holds the crown in place on the watch. And here we are. Look at all that beautiful engine turning. Now here's the workbench where we keep all the parts. We take tape and put it out so that the jelly side is out and you can stick all the parts onto it. And here's another view of the workbench showing all the little screws and everything fastened down on the tape so you don't lose them. The battery is there, the watch case. We fixed the crown, and now it's time to put the watch back together. And here it is going back in the case. The battery's going in. I don't like to touch the battery with my finger. It leaves a fingerprint, and that can lead to corrosion. And then we put the case on the back, and there it is. It's all running and working fine. Snack time. On space station, when it was time for a snack, we would follow Russian tradition and have black bread and honey. This is the galley section in the service module. And the galley table is visible there, and we're opening up a bag of Russian bread. There they are, little loaves of bread. Here's a can of Russian honey, miod. You open up the can. There's no Velcro on the Russian food, so to hold them down to the table, you use that strap that's visible. However, with the honey, it's kind of sticky, gooey. So what we would do is we would use what we learned in college in our surface chemistry class, and we'd put a drop of water on the bottom of the can, and then you would use surface tension force to hold the can of honey down to the table, just like that. Voila. And here we are. The honey drawing out little threads. We put the loaves of Russian bread in there. They're little individual loaves, bite size, scaled down to the right size for a Barbie doll. So we would refer to them as our Barbie breads. You can pull out a loaf and a tractor beam of honey will draw it back in the can. And you can scarf down your bread and honey. Now here is a bag of tea. Now it's not a tea bag, it's a bag of tea, and it's off to the left. And there's a straw that you normally suck the tea out of the bag with. Well, here we're going to use our chopsticks to eat tea. So you squeeze a little hot tea out from the bag, and it forms a sphere on the end of the straw. And then you can use your surface tension forces again to be your friend, and you can just grab a blob of tea with your chopsticks, and then you can eat it. Now notice in the can of honey you have a hemispherical surface profile too. You won't see that in a gravitational setting for something that large in diameter. So here we are eating our tea with chopsticks. Yum yum. There we go. Oops, you spill a drop. It doesn't matter. You just grab it with the chopsticks. And again, surface tension force is your friend in weightlessness. Now here's some peanut butter. And there's nothing better than peanut butter and honey. So look at that. Mix a little peanut butter in with the honey. Oops, we're losing a cracker off there to the right. And then we just mix it in a little bit using the chopsticks. And this is really yummy stuff. It's good on crackers. Oh, yum, yum. And look at that. Kind of looks like a sea creature. And this is an example that in space, you get to play with your food and you can call it science. And now you just dip a cracker in there. And oh, it's really yummy. Well, after you're done with your snack, you have to clean up. And here is what we do for cleaning up. You got to smash your cans. And it's actually sort of a strength exercise. So you smash your can to make them a smaller volume than they normally would be. And then you put them in a wet trash container where they won't get all stinky. That's that little rubber bag down off of the handrail there. You smash them as small as you can. And then the bag there is held on with a big rubber band, and you just pull it off, stick it in the bag with all the other wet wrappers that are contaminated with food, and then you stick the neck of the bag underneath the rubber band, and away you go. And then we have another wastebasket for dry trash, and you can clean up your scissors and wipe off the table and leave it clean.